My name is Will. I work for ARM. I coordinate the compiler development that we do at ARM. And I've got a few slides to take you through what a compiler does and how to make the best use of it in the work you're doing this week. So let's get going. Here's what we're going to cover. A little bit about how compilers work, like I mentioned, a bit of practical stuff about what compilers are available on the AWS systems that you'll be using this week. And then a bunch of detail about how to make best use of compilers using compiler flags, and a bunch of links that we will share the slide deck so you can follow them and refer to some of the information in there through the week. Okay, so what's a compiler do? So you've got some application code, you run a compiler and it spits out a binary and you run it. There you go. Stuff in the middle is kind of a black box. You don't usually need to think about how it works, but it's kind of useful to know a little bit more about what a compiler really does. So we're going to take one example, which is from our commercial compiler, though this holds basically exactly for open source LLVM because our commercial compiler is based on open source LLVM. First of all, you start with the user code, which is what you supply. So for our interest today, this is mostly C or C++ or Fortran. Those are the two kind of dominant languages within the HPC space for compiled code. A honorable mention goes to Python, which is also interesting for a bunch of HPC, but this is not a pre-compiled language. And so the flow that it goes through is a little different. So we're going to focus on C and C++ and Fortran for today. And the first thing a compiler does is it parses all of that code that you have and turns it into what the compiler calls an intermediate representation. So the LLVM compiler has a language, which it calls its intermediate representation, or IR, that allows it to express the intent of any code in any source language that it can compile. Then once it's got it into that form, it stays there for ages and just progressively gets better and more optimal and more target specific. And then eventually you get to the point where you're generating a set of instructions for the machine that you want to run on. But let's pause for a moment on what you do in that middle section. A compiler has three main jobs. The first one is kind of simplifying the world. So this is a process called canonicalization. And the idea is that if you have 12 different ways of representing the same thing, then just use one of them. It doesn't matter too much which one, but you just choose one. The compiler looks for all 12 of those and then modifies the IR to use the one canonical form. And that makes pattern matching later more straightforward. So that's part one. Part two is something called analysis. So these are phases of the compile where you don't change the IR, but you learn something new about it. So maybe a good example is it's important to understand the relationship that pointers have to each other and the memory that those pointers access. Because if you know for sure that two different pointers can't possibly overlap in terms of their memory accesses, then it's possible to rearrange those memory accesses in relation to each other in some circumstances. And so you have analysis passes that do what's called alias analysis to check whether those pointers might overlap or not. And if they don't, then that allows other things to happen. So that's point two. And then the third thing that compilers do is optimization. So it uses the IR in a canonical form that's been analyzed by some other pass and then looks for patterns where it can simplify the IR to something that's more efficient and uses all of that analysis and so on to be able to do that in a kind of structured way. And which of those optimizations are applicable depends on both the source code that's come in, but also the target machine that you're aiming towards. And the way that you tell the compiler about the target machine that you're on is using user-supplied flags. So we're going to concentrate a bunch on making sure that you give a good set of flags for your workload to allow the compiler to do the best job that it can. Okay, so quick pause on what compilers exist for ARM. So we, ARM, have a commercial tool chain that we call ARM Compiler for Linux, which is, as I say, aimed at the high-performance computing space. Then there's also open source compilers. The two main ones that we care about and we contribute to very heavily are the LLVM ecosystem, which has a Fortran front end in development that we're very actively involved in developing the Fortran front end called Flang. So LLVM Flang we contribute very heavily to, and GCC we contribute very heavily to as well. In addition, because of the way the kind of ARM business model works, it's in our interest that end users have the best possible experience of using any ARM-based system, and therefore it's in our interest to help all of the other vendor commercial compilers that target ARM out there. So today that comes down to three main tool chains. There's the Cray HPE tool chain for their systems. There's the Fujitsu's tool chain for their systems, and there's the NVIDIA tool chain for their systems. And all three of those, when they target ARM, are based on LLVM, which means that we've got a common base that we can give code to all three of those to help their compilers work better on ARM. So yeah, those are everything that's available across the system. Now let's focus down on what we have on the AWS systems that you're going to be using, and in particular on the installation of Spack that you're going to be using. I know that some of the Spack folks are going to give a talk, so I won't go into a lot of detail here. I'll just say that we have three tool chains, and they're the most recent versions of ARM Compiler for Linux, GCC, and the NVIDIA HPC software development kit. And all of those are set up in Spack. You should be able to do Spack compiler list and see them. It will also be possible to auto detect other tool chains that are in your path. So if you've got some other tool chain installed, then the way Spack works, you can say Spack compiler add, and it will magically find that tool chain and configure itself to use it. And then, so once Spack knows about a compiler, you use the % notation to tell it to use that compiler when it's installing some workload. So here's some examples of Cloverleaf. So if you want to build and install Cloverleaf version 1.1 with each of the three tool chains that we have available, then you'd use some command that looks a bit like this. And then having done that and they're built, you can say Spack find Cloverleaf, and it will show you three installations, each built with a different compiler. Then it may be that through the week you want or need to use the compilers outside of Spack, in which case you'll use the environment modules that are installed on the system. If you say module list, you'll see a bunch of these. If you say, for example, module load ARM21, this will change your environment on your shell so that the binaries in ARM Compiler for Linux are available in your path, and a few other environment variables are set up correctly to make use of that compiler. And then all you need to do then is look at your makefiles for the workload you're building and set up the variables in that makefile correctly to use that compiler. And there's a table here listing all of the different binary names that GCC and ARM Compiler for Linux and the NVIDIA compiler use when you're compiling each of C, C++, and Fortran. Okay, quick side note around OpenMP. The point here is this is not toolchain specific, so all of the compilers work in the same way. This is part of the OpenMP specification, and all of the compilers support that specification. But these are environment variables you can set, and they'll change the behavior of your OpenMP runtime. OMP num threads sets how many threads OpenMP should spawn when it hits a parallel region. OMP display env is a debugging tool, causes the runtime to print out a bunch of information about the runtime values of the various things that you can configure in OpenMP. OMP procbind and OMP places are both to do with where OpenMP threads are placed on the physical set of cores that you have available to you. On the systems you're going to be using today, it's very likely that OMP places, you just want to set it to cores and forget about it. There's a much more detailed set of arguments you can give that in order to manually place every OpenMP thread on a particular core, but I'm not going to go into that now. OMP procbind is important. This tells OpenMP where to place hardware threads, and not setting this is almost universally a terrible idea, because that says that threads can be placed anywhere and that they can migrate around the place, which is probably bad for HPC use cases. So if you set it to true, then they'll still be placed anywhere, but they won't move. So that's better than nothing. Close is very likely to be what most people want most of the time on ARM systems, and that says that OpenMP threads with that are close to each other in terms of what thread number they are will sit on hardware threads that are close to each other. So that is very good for inter-thread communication. Whereas spread says they'll be placed as far away from each other as they can be on the system, which is good for availability of caching. So I won't go into more detail on that now. There's a bunch of more detailed information in some of the links I'll be sharing later, and there's a bunch of people who are experts at this who will be available on Spack, so you can discuss that with them. And I'm going to skip over OMP dynamic and OMP nested. It's probably not relevant to most people. Okay, now if all of that seems a bit daunting, the good news is that if you're using a framework like ReFrame, which I believe you will be, it has a very good understanding of how OpenMP works and how to set these variables, and does it for you. So if you have a configuration like this one, where you just parameterize it and say that you want, let's say, 8 OpenMP threads and 2 MPI ranks across 2 nodes, then it will distribute your job and set up OpenMP correctly so that all of that just works. Okay, I'm going to take a little sideline for a moment to talk about what the ARM architecture is, and this has an implication on what the compiler can do for you and the instructions it's allowed to use. So at the very core of ARM's business model is we design and license an architecture, or a few different architectures actually, but the core ones that matter for our purposes today are the ARM v8 architecture, which is in the Graviton 2 systems that you're going to be running on, and the newly announced ARM v9 architecture, which will be on systems that come up in the fairly near future. So that architecture has a number of what we call the sort of annual tick. So once per year, we release a new version, and we call it names like v8.5a and v8.6a and so on. And that is a collection of, you can think of them as a collection of instructions or sets of instructions that are defined by the architecture, and any implementation that is compliant with the architecture will implement a defined set of those instructions. And so for each annual tick, you'll have some number of features that are mandatory that you have to implement. If you want to make a v8.5a compatible core, then you have to implement some set of them. And then there's a set of features which are optional, and you can choose to add support for those to your CPU, depending on what your market needs. And that way, the ARM architecture can be really flexible and can serve everything from kind of really small smart devices up to the biggest supercomputer in the world. And in addition to the annual ticks, you have some optional extensions which are bigger, such as the scalable vector extension. Now, that's not supported on the Graviton 2 systems you're going to be using, so we're not going to talk about that in detail today, but just letting you know that's out there. So, as I've mentioned, the architecture specifies roughly what instructions a CPU supports. So that's useful information for the compiler, because if it knows that the system supports a set of instructions and finds some code that could usefully make use of those instructions, then those are the instructions that it might use and get more efficient code. Now, because of some of the complexity that I just talked about you've got our annual ticks, like in the case of the Graviton 2, the base architecture level that it supports is v8.2. So that says that it supports all of the mandatory features of v8.2, and in addition, it happens to support some other extensions. So some of these ones listed here happen to be what the Graviton system implements, which are 16-bit floating point, something that stands for release consistent, processor consistent, atomic lock instructions. It's not totally important what that means today. Dot product instructions for doing dot product operations on registers, and crypto instructions, which are for doing things like AES and SHA calculations for cryptography. Now, that's a mouthful and far too much information for a general user to know. So we make a set of flags that simplify it, and you can specify exactly what CPU you're using, and the compiler knows what that means in terms of the architectural features available to you. So you can say -m CPU equals Neoverse N1, which is the ARM designed core on which the Graviton 2 is based, plus cryptography, because the Graviton 2 instantiation of the Neoverse N1 core has the cryptographic extension on it. Or, even simpler, you can say, work out what you're on right now while you're compiling and use that architecture. So -m CPU equals native introspectively looks at the core that it's compiling on and says, I know what this is. This is a Neoverse N1 with crypto support, so I'm going to enable all of those architectural features, and you're done. Quick example of why this matters. In v8.1, there's an extension which improves the way that atomic locking is done on systems with lots of cores. And when you've got lots of heavily threaded code, like you have in OpenMP workloads, this has a huge impact on how efficient the OpenMP runtime is when it's dealing with shared resources across multiple threads. And if you built your OpenMP runtime without this, it would have a really bad degrading impact on how well your code's performed. So we don't. So we ship an OpenMP runtime that works out at compile time that you're on a system that supports this, and you use the good one because you're on a Graviton 2 system which supports this feature. And also compilers now have features in them where they can, when they get locking code that needs to use these instructions, actually make two versions of it, and at runtime work out which one is the best one to use, because it has such a big impact on pthread implementations and OpenMP runtimes and so on. Okay, then there's one other advantage you get when you say -m CPU equals native, which is the compiler has an inbuilt understanding of the latency and throughput of every instruction on your particular core. and it can use that to decide what instructions to use. So if you had one instruction that's quite expensive on a particular core, or another instruction that's much cheaper, but maybe you needed a few more instructions, the compiler can reason about which of those two forms is better and choose the best one for the CPU that you're running on today. So all of that boils down to just add minus m CPU equals native. For some use cases, this is not a good idea. Like if you needed to build code on one machine and run it on several other types of machine, this is too simplistic. But in HPC, we basically never do that. You compile code for the machine that you're looking at today, and then you run it on that machine, and you want the best possible performance. And so minus m CPU equals native is perfect. So now we've got that locked in, the next thing to think about is the optimization level you want your compiler to perform. So for most compilers, you give that with a minus capital O and then a number. There's a table on the next slide that gives a bit more detail on that. But what you probably want to do is one of these three things. So either you want to give minus O fast, or minus O3 with some other flags, or just minus O3. And which one of those you choose depends on your workload. So minus O fast gives the compiler a heap of freedom about reordering things like floating point instructions in a way that isn't universally safe. It isn't in strict compliance to the IEEE floating point standard. But when your algorithm doesn't need you to be in strict compliance to that standard, then it allows the compiler to plant code that's significantly faster. So this isn't universal. It doesn't work for everything, but it's worth trying for almost everything. And then if you're finding that the results that you're getting are incorrect or inaccurate, then you need to tone down your optimization level. So then that's option one. Option two is a sort of halfway house. So minus O fast actually enables 7 different things in the compiler. I won't go into what all of them do, but there's a subset of them, which are the 3 listed here, which are to do with associative math, that is the ability to move around floating points operations in relation to each other. So it's called reassociation. Whether or not you need to correctly represent the signedness of 0, and whether or not you need you have exception handlers registered for floating points that you do something with. And for a lot of high performance computing codes, you won't do that. And these will be a perfectly valid set of flags to give. And if you give these 3 together, then it enables the compiler to do some really useful optimizations. So things like if you have reductions in your code, you can create a significantly more efficient version of those when you have these flags enabled. Then option 3 is what should be considered your sort of base level compilation for HPC, which is O3, which is compile as aggressively as you can, but stay in compliance with IEEE floating point behaviors. Then, okay, so you want to choose one of those 3, and then you want to consider, in addition, giving this flag, which is minus F, FB contract equals fast. What that says is you allow floating point contractions, which means you allow the compiler to take pairs of floating points operations, such as multiply 2 numbers together, then add them to a third, and contract them into a single instruction. So we have instructions to do that as a single floating point operation. And because it's so common within floating point code, then that can have a really big impact on your code. Again, this will give you a very minorly different result than not doing that in terms of your floating point result, but the impact on that is quite minor. And it's allowed by the Fortran language, so it's enabled by default on ARM compiler for Linux's Fortran compiler. but it's not enabled by default for C and C++, because the language standard doesn't tell you that you're allowed to do that. So if you're not using -O fast, then it's probably a good idea to try adding this. And you can check whether or not it has a negative effect on your accuracy, but that is probably a safe thing to do. Final thing I wanted to mention is a thing called link time optimization. So if you imagine that you are building multiple objects as separate compilation steps, and then you link them all together with the linker as the last stage of compilation, if you don't have this flag, then if you have a function call in one of those objects to some function in another of those objects, then the contents of that function are a black box to this object over here. So it can't make any assumptions about it. It can't do any optimization based on the what's happening inside of that function. What link time optimization allows you to do is it allows the compiler to see between the separate compiled objects at link time and do optimizations across them. And that can have a really big effect on the performance of some workloads. So for LLVM-based compilers, this is a pretty mature technology. It's used by default in a bunch of spaces that LLVM is used in. And you give this -FLTO option to both the compiler and when you're linking, and it magically does it for you. So that's worth trying. Okay, reference slide. I won't spend too long on this, but just I've got a column here that shows the behavior on Intel's compiler in case that's something that you've used in the past. And then columns for our commercial compiler, GCC, and NVIDIA's commercial compiler. And we talk about optimization level flags, how to enable fast math, enabling -M CPU equals native, which I've talked about. Enabling OpenMP is mildly different for NVIDIA. Making use of vendor math libraries, so BLAST, LPAC, FFT, kernels, that sort of thing. How to enable debug, which for all of the tools chains you'll be using is just with -G. One thing of note is if you're using a very heavy optimization level, then the compiler really messes around with the original source ordering of your instructions. And so debugging that is quite difficult. So if you need to debug your code, you probably want to tune down the optimization level down to maybe 01 or so, alongside with -G. And that will mean that your debugger has a better chance of understanding the relationship between the source code and the instructions that it's executing. Then finally, you can ask the compiler to give some diagnostic outputs about what it did and why it made that choice. On GCC, that's -F opt info vec will give you information about vectorization. On LLVM-based compilers, which include the NVIDIA compiler and ARM compiler for Linux, you give an option of -R pass, and then you specify some string. And each of the phases I talked about at the start of where the compiler takes its IR and looks at it or modifies it in some way, those are called passes. And what this says is that you want to enable the remarks or kind of diagnostic outputs for a set of passes. And so the string you give is the name of the passes you want to enable it for. So when I've said loop here, that partially matches against the loop vectorization pass and also the loop unrolling pass. So when you give -R pass equals loop, you'll see a bunch of output as you compile that says, here's the decisions I'm making about each of the loops that I'm seeing in my code. And then if you want to dig even deeper into that, there's similar flags to say, give me information when you didn't manage to vectorize a loop or unroll a loop, and give me information about what you were reasoning and what you were thinking about when deciding whether to vectorize or unroll or not. Okay. So finally, we've got a bunch of links on this slide. We'll share the PDF of these slides so you can follow through on them. But we've got links to the list of all the command line options available on all of the tool chains that you have, some guides to porting. If you've got x86 code that's got intrinsics in it, which are specific to the x86 architecture, you need to make versions of those for Neon, which is the ARM vector architecture that's available on the Graviton systems. So we've got links to a blog post about how to do that, and a searchable online guide for finding the right Neon intrinsic for whatever it is you're trying to do. Then our developer.arm.com HPC section has got a whole heap of material that goes through the same sorts of things I've covered today in a bunch more depth. So quick reference guides, full weight reference guides, a walkthrough of porting and optimizing for ARM, and a guide to OpenMP thread mapping, plus a bunch of other stuff as well. So hopefully that should give you a good start on what you need. And then if there's anything you still can't find, then Slack is the answer. So here's links to a bunch of the help channels on Slack where folks from ARM and AWS are going to be hanging out and answering your questions. Cool. So that's all I had to say for today. Good luck. Hope you have a great week, and I will see you on Slack. Bye.